Hello, Bob Rasuli, Orange County, California. Many of you preparing for the API 580 exam have asked me to unpack probability of failure, or POF, in a way that is clear and practical, especially with refinery scenarios. In risk-based inspection, RBI, probability of failure is about likelihood. When we assess probability of failure, we are asking how likely this equipment is to lose containment in a given time frame. Not how severe the outcome would be, that is consequence, but whether it will fail and how often. Let us ground that with examples. Imagine a crude unit overhead line in wet service with corrosion under insulation, CUI, as a credible mechanism. If no one has opened insulation or screened it in years, the probability is higher because the deterioration rate is unknown. If guided wave or ultrasonic screening was recently performed and healthy thickness confirmed, the probability drops. Same line and same environment, but different probability based on inspection effectiveness and data quality. Probability can be expressed as a frequency or as a category. You might see a value like 0.001 failures per year, about once in 1,000 years. In qualitative assessments, it is often low, medium, high, or remote, occasional, frequent. For instance, an FCCU main fractionator column that was recently cleaned, internally inspected, and repaired could be low. An older caustic injection line to a desalter with a history of leaks and sparse inspection might be high. Now, assessment approaches, a qualitative POF uses engineering judgment and subject matter experience. If a crude overhead line has not been checked under insulation in many years, you can conservatively rate probability higher because CUI is credible and the condition is uncertain. A quantitative approach pulls from failure frequency data and adjusts for your service, materials, and age. For example, you can use industry data for exchangers in HF alkylation service and tune it for your unit specifics. Semi-quantitative is the middle ground, combining some calculations with categorical inputs, often supported by RBI software. How do we determine probability of failure in practice? This is where mechanisms, deterioration rates, and inspection effectiveness come together. Consider a heat exchanger in HF alkylation service. Credible mechanisms include HF corrosion and hydrogen blistering, with potential cracking at susceptible details. If inspections are targeted, for example, profile radiography, RT, on welds and ultrasonic mapping, UT, at high-risk locations, uncertainty shrinks and probability goes down. If coverage is minimal or outdated, probability goes up, even though the service has not changed. Another case is a hydrotreater piping circuit where sulfidation is active and localized. A handful of spot thickness readings can miss the deepest thin area, so the effective probability is higher than expected. If you scan with automated UT mapping or use profile RT at elbows and Ts, your likelihood of detecting critical thinning is much greater and the probability drops. Let us return to that caustic injection line feeding a desalter. Injection points see turbulence, mixing, and local pH swings that accelerate corrosion. If the inspection plan ignores those locations, the line probability rating should be high. Focused UT at the injection point and downstream elbows can validate condition and justify lowering probability. Probability is not only about corrosion or cracking. External events matter. Think of storage tanks in a coastal refinery, where hurricanes and flooding can increase probability of failure from external loading. Compare that to a refinery located in a region with very stable ground and low extreme weather exposure. The same tank design faces different external probability drivers. Operator error or instrument malfunction can also influence likelihood, reminding us probability is broader than a single wall loss rate. Keys for success when you assess probability. Always identify all credible mechanisms and do not stop at the obvious one. A crude heater tube might face sulfidation on the process side and fuel side corrosion simultaneously. Understand interactions. Hydrogen damage can weaken material and accelerate cracking susceptibility. Use equipment-specific data whenever possible. Your inspection data is stronger than generic averages. Document how inspection effectiveness changes probability. Weak plans mean higher POF. Exam reminder. Probability of failure is about likelihood, not severity. It can be expressed as frequencies or as categories. You can assess it qualitatively, quantitatively, or semi-quantitative. It is driven by mechanisms, deterioration, inspection effectiveness, and sometimes external events. If you can explain those points clearly and illustrate them with refinery scenarios such as crude overhead lines with CUI, FCCU columns with sulfidation, caustic injection piping with localized corrosion, and HF exchangers with weld attack or blistering, you will be ready to handle probability questions with confidence. To close, probability of failure is not a single number. It is a disciplined way of thinking about likelihood. Carry that mindset into your RBI work and into your exam preparation.